Welcome to Calculus 2, everybody. At this point in your studies of calculus, you've probably looked at differentiation, a lot of differentiation, of a lot of different types of functions, polynomials, trig functions, to name a couple, probably quotients, rational functions, I should say, at least some. What we want to see in this second piece of the calculus course is, at least to begin with, expanding that catalog or encyclopedia of functions that we can take derivatives of and or integrals of. So we want to still study differentiation and integration, but we're going to look at just broader and broader classes of functions. And think of it as essentially adding to a function library, different types of functions, and being able to take their derivatives and find antiderivatives. So if you think about what's missing in your arsenal at this point, the first might be exponential functions. And so that's where we're going to start. And a natural piece to follow then will be logarithmic functions. So since exponential functions and logarithmic functions are inverse, let's begin with a brief review of inverse functions. All right, so our review of the inverse function, we're going to start with this motivation problem, and we'll answer it in a few lectures from now. But let's suppose that we have a population of bacteria that is growing according to this model right here. N of t, number of bacteria, function of time, is 20 e to the t over 3, where n is the number of bacteria present, and time, t, is measured in hours. A person is going to become ill when the number of bacteria in their system exceeds 275. So the question is, after how many hours will a person with such bacteria present become sick? Notice that this is indeed a question of the inverse, because 275 is essentially the value of n, right? But this is a function whose input is t. So we're given an output, we're looking for the value of the corresponding input. We need an inverse function. Okay, well, what is a function? Let's just start with that. Well, first of all, it is a relation between two sets, D and R. D, of course, we refer to that as the domain, and R as the range. And it's done in such a way that each element in D is mapped to exactly one element of R. What do I mean by that? Well, let's say that this is my set D. Let's say that this is my set R. And I don't know, maybe D is 0, 2, 5, 9. And maybe R is 3, 1, 7, 5. And let's say that 0 gets sent to 1, 2 gets sent to 3, 5 gets sent to 7, and 9 gets sent to 5. Notice that every domain element goes to one output. 0 is only mapped to 1. 2 is only mapped to 3. 5 only to 7. 9 only to 5. This is a function, okay? Now, on the other hand, if maybe I had this situation, maybe my domain was 0, 1, 2, my range was 5, 6, 9, 3. Let's say 0 got sent to 5, 1 got sent to 6, 1 also got sent to 9, and 2 got sent to 3. Well, now an input of 1 gives me two different outputs, right? 1 gets mapped to 6 and it gets mapped to 9. So this is not a function, okay? Now, a natural question to ask is, when can we go the other way, starting with the range, going back to the domain and have that be a function? And so what we need to know first is there an additional condition that we need to impose for the inverse function to exist? After all, if you have a domain and a range, F is going to be the rule that assigns elements from D to R, but the inverse goes back the other way, okay? Well, in other words, we would need each range element to come from only one domain element. You see, if I had this situation, whoops, I'm sorry. If I had, say, have an x1 and an x2, and I have a y, I could have x1 and x2 going to the same output. That's okay, right? That would still be a function. But if I want to go back the other way, I've got ambiguity now, right? Where did y come from? Well, it came from x1 or x2. Which one? I don't know. So that can't happen, right? For the inverse to exist, we need every input to go to only one output and every output to have come from only one input. That is known as one-to-one. F needs to be 1 to 1. And what do I mean by that? I think this kind of builds an intuitive idea of what 1 to 1 means, but what's the actual definition? Well, f of x1 does not equal f of x2 whenever x1 does not equal x2. If you want to put this in layman's terms, different outputs come from different inputs. Okay. If I have two different outputs, I know they came from two different places to begin with. Okay. All right. So let's decide if the given function is 1 to 1. So f of x equals 2x cubed. Well, we know from the graph, right, that essentially looks like this. So f is increasing. And if f is increasing, then it's going to need to be 1 to 1. We haven't proved that, but it kind of appeals to your intuition. So f is 1 to 1. Don't worry, we'll prove it in a moment. Okay. How about x squared minus 2? Well, we know that this graph looks like a parabola, right? And by looks like, I mean it actually is. X squared minus 2. Well, gee, here are, right, two of the same outputs rather, coming from two different inputs. So we could do this a couple of ways. We could say g of 1 equals -1 and g of -1 equals -1. So g is not 1 to 1. Because again, I showed that the definition fails, right? I found two inputs that give me the same output. That violates the definition of 1 to 1-ness. How about sine x? Well, we could play the same game, right? F, excuse me, f of pi halves is equal to, well, f of what? Well, I could go around the circle again, right? F of pi halves is equal to 1, but that's the same as f of 5 pi halves. So it's not 1 to 1. Similarly, you could say f of pi fourths, root 2 over 2, is equal to f of 3 pi fourths. Different inputs, same output. So here, again, not 1 to 1. And of course, we also know the graph, right? We know that sine does this. Okay, and so we can find here lots of inputs that give the same output. Okay. What about this? Notice what's happened now. Now I have a domain restriction, which means instead of looking at the entire graph of sine, I'm only looking from negative pi halves to pi halves. Oh, so in this case, f is 1 to 1, right? There is not a single pair of inputs that give the same output. So f is 1 to 1. So let's prove that if a function is strictly increasing, then it is 1 to 1. Let's think about what this means. You know, I think there's an intuitive picture, right? If you see an increasing function, right? Maybe this is my x-axis. Then you just see that as you move right, the y values move up. And so they can't share a value. Once you increase the x value, you're going to also increase the y value. They won't be the same. While that's a wonderful intuitive notion, it's not a rigorous proof. And so what I'm going to do is I'm going to prove by what's known as the contrapositive. I'm going to suppose that f is not 1 to 1 and show then it could not be strictly increasing. So suppose f is not 1 to 1. Then there exists x1 and x2 unequal such that, f of x1 does not equal f of x2. I'm sorry, I said that backwards. Such that f of x1 equals f of x2, right? We're saying f is not 1 to 1. So I can find a pair of distinct x values that give me the same output. Well, as soon as I say this, that violates my hypothesis, right? Then f must not be increasing, okay? The logic here is that if the logic here says that A implies B is logically equivalent to not B implies not A. So we've actually done this. And you're going to find throughout this course that I do prove a lot of the theorems I state. Not all of them. Some of the proofs are slightly beyond the scope of the course. Reserve those for you math majors in your first analysis courses. But a lot of things will be proved, and I will touch on some techniques as I go through them. If those who are interested, the logical apparatus I used was contrapositive, okay? All right. So let's suppose f is 1 to 1 with domain D and range R. G is the inverse. If when I compose G and F, I get X for all X, f of X in B, and I'm sorry, for all f of X in the range R. Okay, when we denote the inverse G as F inverse. This F -1 does not mean 1 over F. This is nonsensical. This little -1 means inverse. It denotes inverse, okay? So don't ever do this. This makes me sad when I see that right there. So no, okay? Well, what are the domain and range of an inverse function? So we know what an inverse function does. The function maps D to R, and the inverse maps R back to D. So the domain of F inverse is the range of F. The range of F inverse is the domain of F. Okay? All right, moving on. Find the inverse function. Well, if we're swapping domain elements for range elements, then, if I change my f of x to y just for ease of notation, then I'm really interchanging, right? I'm saying what was an output is now an input and vice versa. So I have x equals y cubed minus 5. And then we just solve for x. I'm sorry, we solve for y, right? X plus 5 will be y cubed. I turn this around just to make it look better. Y cubed equals x plus 5. And so y will be the cube root of x plus 5, which I'm going to rename as f inverse of x, it's the cube root of x plus 5. Okay? How about this one? 2x squared minus 1. You may be saying, hey, wait a second. That's not 1 to 1, so it is not, can't have an inverse, but be careful. We've restricted the domain, okay? So when we look at 2x squared minus 1, our x's are less than 0. That means we're only looking at the left side of this parabola. We've gotten rid of the right side. Well, let's play that same game. X equals 2y squared minus 1. X plus 1 equals 2y squared. Might as well do this while we're at it. I'm going to divide by 2. And then take the square root. Is that right? Well, careful. Really, whoops, didn't mean to do that. Really, when you have y squared equals, you get plus or minus, right? Well, that's where this domain restriction comes in. Plus or minus, which one? Minus, okay, minus. Right, because I'm looking at the left side, okay? So what is the coordinate geometry of inverse functions, right? If I have, say, this function, then really what's happening is this is a point, and this is a point, and this is a point. Right, we're swapping x's and y's. So what's going to happen is we're going to get this other thing that looks like this. The swapping of the x's and the y's is really a reflection over y equals x. So a function and its inverse are symmetric over the line y equals x, okay? So if this were the point, say 3, 2, then this would be the point. That's a bad example, but 2, 3, right? There's 3, 2. That point over there would be 2, 3, okay? If you have the point 4, 1 on F, then 1, 4 is going to be on F inverse, and so on, okay? All right. So at this point, we've really done no calculus, right? So what we want to do now is actually look at what the calculus of inverse functions might be. And the first is this. Remember the big issues of calculus. What are the big ideas, right? Continuity, differentiability, integrability. So let's start with continuity. If f is a one-to-one continuous function on its domain, then its inverse is also continuous. And I'm just going to tease you. The proof is a little bit beyond the scope of the course. If you remember from back in the days, you're going to use an epsilon delta technique. You have to get to the precise definition of the limit because that's what continuity involves, right? So it's in the back. You can find it in the back of any textbook, or if not, no big deal, but it's a little bit beyond the scope of the course. So I'm going to actually omit the proof as much as it hurts me to do so. So just, take the conclusion, right? If you have a one-to-one continuous function, the inverse is also continuous. All right. This tells us how to get the derivative of the inverse. So if f is one-to-one and differentiable with inverse f inverse, and f prime of f inverse of a is not 0, so that this denominator is not 0, then we have f inverse prime of a equals 1 over f prime of f inverse of a. Let's prove this. And so what I'm going to do is I'm going to say, I'm going to let f of b equal a, and y be f inverse of x, okay? F is differentiable so it is continuous, okay? Thus, f inverse is continuous. All right, now, let's see. So if we have x approaching a, then that really tells me that y is approaching b, right? Another way of thinking of that is that f inverse of x is approaching f inverse of a, okay? And so at this point, oops, sorry guys. At this point, we're going to actually start applying some definitions here, okay? So f inverse prime of a. We know the limit definition of the derivative, right? F inverse of x minus f inverse of a all over x minus a. Well, this is just the limit as y goes to b, right? Because f inverse of x is y. F inverse of a is my b. So y minus b over f of y minus f of b, okay? And this may seem a little bit like a cheap shot, but I can write this as 1 over, I'm going to not skip a step there. I'm going to call this the limit as y goes to b of 1 over f of y minus f of b all over y minus b. Well, this denominator should look very familiar, right? This denominator here is itself f prime of b. So I have 1 over f prime of b. Oh yeah, what was b? 1 over f prime of f inverse of a. And that proves it, okay? Now, to be fair, this is probably a class where you're going to see more proof than you're perhaps used to. So you're going to, as you work through my proofs, you might come to a point where you say, gosh, I never would have thought of that. And that's okay. I don't want you to try to memorize these. Instead, I want you to see the logic that threads through them. So what are the big logical signposts here? Well, here at this point, I'm just using the definition of the derivative, right? The limit definition of the derivative at a particular value of x. And then I'm manipulating what those values are, right? I've established some relationships and some notation up here, and I'm manipulating that. I know that I want to get my hands on a derivative, f prime, right? And I need that to be in the denominator. So what I'm doing as I go from, say, this step to this step is really just engineering that denominator to work out the way I hope it does, which it does, and all is good, okay? All right, so let's use this. Find f prime of f inverse of 9 given, and we're going to need to add a little bit of information here. All right, given f inverse prime of 9 is equal to 2. So we know that f inverse prime of 9 is equal to 1 over f prime f inverse of 9. I also know that that's 2. So this just becomes simple algebra, right? F prime of f inverse of 9 then would have to be equal to 1/2. Okay, so that's just simple application of the formula that we just looked at. All right. All right, guys. So we did a very brief, rapid review of inverse functions. Hopefully most of that rang a bell. And then we introduced a little bit new material by talking about the calculus involved with inverse functions. Very briefly though, you know, I started this lecture by mentioning that we're expanding our library of functions that we can differentiate and integrate. And you might be wondering, well, why are we starting with inverses? I'll answer that question. You know, we're going to look at exponential functions, and it turns out that there's a relationship between exponential functions derivatives and their inverses. And so we start with the inverse functions so that we can develop our differentiation of the exponential function completely and fairly efficiently once we're equipped with this formula. So with that, I will encourage you to go back and review anything you need to review. Make sure you work some problems because that's where things really become your own. And until we meet again in our next lecture, I wish you happy studies.